Welcome to the MR physics class on MR coil design. So through the class and through your studies that you do with magnetic resonance, you're going to hear about coils. So just in general, what do they look like? When you walk into the scan room, what are you likely to see? This is a photograph of our 3T Prisma scanner made by Siemens. And on the bed, there are two coils. Here's one that's placed. It's ready for the subject to arrive. And the top comes off. The person can lie inside of it and put their head in it, and then we put the top on. It's open in the front, and all this kind of material on top, it's a mirror so that they can look at pictures and videos as part of a functional study. Here is a second coil. Not to be used at the same time. This would take the place of that one. I just put this here to make it a little easier to see. Here's another view. There's the first coil that's ready to be used. Here's the second coil on the bed. See the top part can lift off, and back here is a cable that connects the top. So the whole thing is the top and bottom work together as a circuit, but they have to be plugged in together. Here's a video. We'll walk around and get a better idea of both coils. Let me show that again. While we're there, see back here, this blue light, that's the screen that's being shown into this mirror. So with some mirrors, you could do a lot of things in conjunction with the coil. And note that here, this coil, and the other one you can't see so well, but the coil is open. So people can see, can look out. That improves somewhat the situation with claustrophobia. Okay, so another thing is vocabulary. I've been hearing from people taking the course that there are a lot of words, a lot of new words. It's almost like another language. Jargon, we'd say. And you're going to hear about a lot of different coils. So we have names for a variety of these coils that we'll be talking about today, a variety of names. Most commonly, you'll just hear it called the coil. If you arrive one day to do your study and say, oh, the coil is broken, or the coil is ready, the coil is in the magnet. They're going to be talking about this particular kind of coil, which is the radio frequency coil, the coil that we use to apply B1. And it's called a coil because, imagine, forget about science for a minute. If you have a coil of anything, a coil of wire, if a snake is coiled, it's wrapped. And many of these are wrapped in this particular configurations. Most of them look nothing like a wrapped up snake or a coil of wire, but they're still called a coil. So the radio frequency coil is called that because we apply an oscillating magnetic field that has a frequency that's in the range of radios. It could be called the probe. A detector said, oh, which detector did you use? Someone may ask you that. They mean, which coil did you use? They could be called a transmitter because we transmit B1 to the sample, or transmit coil. They're also functioning often as a receiver. So we have to have some kind of a receiver to observe the oscillating magnetic field that is created by the net magnetization in your sample. And a receive coil. Well, often the transmitter and the receiver are done through the same coil, the same set of conductors. But there are many cases where they are not. You may transmit with, say, a very large coil and receive with a small coil that's localized around your region of interest. When they are together, they may be called a transceiver. So all of these words you may hear, and they all are related to radio frequency coil. Now note that they're different from the many other coils we have in NMR. There's gradient coils, shim coils, and a B0 or B0 coil. That's what runs the magnet. Or sometimes there's an extra piece, an extra coil that helps to maintain the magnet stability or set it to a particular place. But these are all different from these many names for the radio frequency coil. So we'll talk first about what the role of the coil is, the parameters that go into making a coil, and then types of MR coils. So in the first role of the MR coil is the transmission. We applying the radio frequency B1. That's the B1 that's oscillating at the Larmor frequency. That causes the net magnetization that's oriented along the z-axis, along the bore of the scanner. It causes it to rotate. And we try to put some component of it, to observe, we put some component of it into the XY plane. We may do many other things with it other than observe, but primarily this is the function. And in this regard, the coil functions as a transmitter. When we are ready to observe, we turn off our transmission, and after a very brief delay, we open the receiver and observe the magnetization as it precesses in the XY plane and returns to the z-axis. As long as we have, remember what's in the XY plane, as long as it maintains phase coherence before it spreads out and randomizes itself, we can observe a signal. That signal comes because this is behaving as a little magnet or oscillating, creating an oscillating electric current in our conductor, which is our NMR coil again. And in this regard, it's functioning as a receiver. So if we have them both together, they're called a transceiver. Now, how does that get transmitted to and from the sample? We've talked about it different times, but we'll talk a little more about it now. So on the transmission side of things, when we put electric current through a wire, it generates a magnetic field, which here is, in this case, we're calling it's the B1. The field lines wrap around the wire, and this is actually true if you just take a wire, it goes to your lamp. If it's not shielded, there will be a magnetic field around that lamp, around that wire, and it's not going to be very strong, but it exists just from the current. And by the right-hand rule, if you put your thumb, you'll take your right hand and put your thumb in the direction of the current. Your fingers will wrap around like they would wrap around the wire. The wire goes in the direction of your fingertips. So this is the direction of the B1. If you run the current the other direction through the wire, then you would have to flip your hand around, and these arrows would all be going in the opposite direction. So the magnetic field, it's not just that there's a magnetic field that exists, it has an orientation, just like a magnet you buy at the store has a north-south orientation to it. So if we run an oscillating electric current through this wire, we will get an oscillating magnetic field. When the current goes this way, oscillating means it goes this way, and then this way, and this way, and this way, back and forth. And so this magnetic field around the wire is going to oscillate back and forth along with the current. Now imagine, I'll show you a photograph actually of something that looks like this in real life. If you have a loop of wire that's, I don't have a connection here for it, but if you put it in a connector with a voltage source, if you have a loop of wire and you run electric current through this loop of wire, it's going to create a magnetic field that goes down through the center of the loop. Imagine you take your right hand and pretend that you are wrapping it around this loop of wire. Your fingers are always going to point down through the center of down toward the center of the loop. That's the direction the B1 field will go. And this sort of configuration is actually called a surface coil. Some of the first measurements in vivo were done with this arrangement. If you put it up against the side of a head or your finger or something, you can get a very sensitive view of what's in the about 1 coil radius into the tissue. So this is a very simple coil. Okay, now how do we how do we get a signal back? Well, after we turn off the receiver, you have this coherent magnetization oscillating in the XY plane. It's generating a magnetic field, a B1. Well, we don't call it B1, but it's another B field. Very faint, but it's exerting a B field from the sample at the Larmor frequency. And as you've heard in another lecture, um, there are all kinds of little magnetic fields being generated, but we can tell this one from the rest because it's oscillating at around the Larmor frequency. And so just as the right-hand rule applied for generating magnetic field, now if you put your fingers around this yellow wire in a way that points them together with the red arrows, it'll show you which way the current's going. So the current would point out where your thumb is going. If this is your right hand wrapped around, you have your fingers here, and your current goes up this way. Well, what's coming from the sample is oscillating at the Larmor frequency. So it means it's going positive and negative at hundreds of millions of times a second. So this field is going back and forth. That means you would have to be flipping your hand back and forth. Your thumb would go up and down and up and down. The current will go back and forth at the Larmor frequency also. And that is what we pick up through the receive path. There's the current. And now we get a B1 field from the sample. And it looks just the same as what we had a moment ago. There's the B1 generated by the wire. And here we have the B1 field, or a B field, we'll call it. I just need to not call it B1 because B1 is only something we apply. But there's an oscillating B field from the sample, and now that is generating current in the wire. So this goes both directions. It's called reciprocity. So let's take another look at this description. Here's the B0, the large magnetic field, say 3 Tesla. And while we're at this, I've been saying 123 megahertz. If you take 42.57 megahertz per Tesla and multiply that by 3 Tesla, you're going to come out with 127 or 128 megahertz. The many magnets are listed as 3 Tesla, but they're actually, like the Siemens magnets, are at least often they're at 2.89 Tesla. So we end up with 123 megahertz that you'll actually be using when you run something on a 3 Tesla, one of the 3 Tesla scanners downstairs. Now but we have, back to this thing, we have a magnetic field, possibly 3 Tesla, or 4 Tesla, whatever system you're on. It creates a net magnetization along the z-axis. Now here's our spectrometer. That's for transmit and receive. When it's in transmit mode, hooked up to our coil here, you get a pulse that comes out. That pulse, I've showed you, is kind of a sinusoid. Imagine that's going at the Larmor frequency. It creates, you're putting through an electric current, and it's going to create a magnetic field wrapped around the wire. As the current oscillates, the magnetic field direction oscillates. And that goes on for, 500 microseconds, a millisecond, however long your RF pulse is. Okay, now, when we did that, we tipped the magnetization into the XY plane. And it's relaxing back. It's processing. And that is creating a magnetic field around the wires, and that is causing an electric current that oscillates at the Larmor frequency. And so that goes back to the spectrometer as our signal. Very weak, microvolts, but very weak. Okay, so how do we get this coil to behave this way? So far, it sounds like you could just take any loop of wire and put it near a sample in the magnet, and as long as you don't have iron in it, you'll be good to go. But that's not really the case. We have to have this coil function very efficiently. We want it to function extremely efficiently exactly at the Larmor frequency. And to do that, we need to, we could call it the resonance frequency also. We need this coil to resonate at the Larmor frequency. To do that, we use something called an RLC circuit. If any of you had physics in high school or college with electromagnetism, you would have heard of RLC. And this is called a resistor. You notice this diagonal squiggle. That's actually the standard symbol for a resistor. It looks a little bit like what you would see if you open up your toaster and look inside, because it's a resistive wire designed to get very hot when you run electricity through it. This loop of wire looks like a coiled snake. That's standard symbol in electronics for an inductor, it's called. Because it's called an inductor because it can induce a magnetic field. Or electric current induces a magnetic field around the conductor. And typically this is what is around our sample, because we want something that's going to create a magnetic field. When we put these two things together, they can really interfere with the sensitivity of the circuit. And as we go along here today, you'll see why. To make it resonate, to minimize the interference, we have to compensate with something called a capacitor. That is called a capacitor because it has a capacity to hold an electric charge. The standard symbol are these two lines. They represent actually metal plates. So if you've ever shuffled across the floor in the winter, having a dry day, and you build up an electric charge on yourself by stripping electrons off the carpet, and you get close to, in my case it was my brother, but what's better is maybe a light switch, and you touch that object, and when you get close enough, you can't stand across the room and expect a spark to jump from your finger to the light switch. You have to get closer and closer, and when you get close enough that the air cannot insulate you from the grounding of the electric circuit in the house, a spark will jump from your finger. But until that spark jumps, you are functioning as a capacitor. You're holding an electric charge. So you can, some old electric circuits actually did this with two plates separated by air. And now in the photographs I'll show you, you'll see plates separated by a layer of ceramic. So we have a resistor, an inductor, a capacitor, and then finally a voltage source. Here's the standard symbol for a voltage source, and that is our radio frequency amplifier. So to get into how we're going to use those R, L, and C, we'll talk about voltage, current, and resistance. So voltage is an electric term that is it's called an electric potential. And you can make it analogous to water in a pipe. And I'll explain in a picture here in a moment, but the I is a standard symbol for current. R is resistance. Voltage, current, resistance, VIR. So if we have a pipe with water source up at the top, and it's the voltage is analogous to how steep an angle the pipe has. If you have a pipe that's completely horizontal, then the water may run out of the ends of the pipe, but there's going to be no net flow from one end to the other. There's no difference in potential energy from one end of the pipe to the other. So a completely flat pipe would be like having zero voltage, a dead battery. If you had a totally vertical pipe, you would have very fast flow. I is the amount of flow, the water going through. R is the amount of resistance to the water. Suppose you had a very rough pipe that's had a lot of friction inside of it. The water wouldn't flow through so easily as one that's very, say, coated with Teflon. Now, if you raise the voltage, if you make the pipe steeper and leave the configuration of like the texture of the pipe the same, you have the same resistance. It's the same diameter, same texture, same resistance. But if you raise the voltage, you can imagine a lot more water is going to flow through it. A lot more electricity will flow through. And V equals IR. So if you double the voltage, you double the current flowing through it. So if we double the voltage coming out of our radio frequency amplifier going through the circuit, we double the amount of current flowing through the coil. Now, If you lower that same pipe, make it more horizontal, now we've got maybe some fraction of the voltage, same resistance because it's the same diameter, same material in the pipe. The current is much less. V equals IR. If you have half the voltage, you have half the current for a given resistance. And then there are cases like if the coil is actually damaged, this happens sometimes. Something breaks, or the connector's not seated properly. Then that's like having one end of the water pipe blocked off. You have infinite resistance. You get no flow. Doesn't matter what the voltage is. If the resistance is infinite, we get no flow. But typically, so resistance is measured in ohms, actually electric resistance. So if we have just some standard resistance, we'll say 100 ohms, you get a level of current. If you cut that resistance dramatically, you get a whole lot of current. Maybe the resistance could be because you've made the pipe smoother inside, or you've increased the diameter of the pipe. So it's a lot easier for the water or the electric current to flow through it. Actually, this is a principle we have with our superconducting magnet. We want zero resistance, and that way there's no impedance to the electricity flowing through the wire. So the current is whatever we put through it, that's what we get. And it just stays that way for years. But when we're talking about an electric circuit for an MR coil, we want to have a particular, we want to have low resistance. All right, we're getting there. As far as the Larmor frequency, we want to look at how each component of the circuit behaves when we have different frequencies. At the top, we have a large current with a small resistance. At the bottom, we have a small current with a large resistance. That's just like the water pipe. So a resistor behaves the same across frequencies. You can have zero frequency, just a steady current like you get out of a DC current coming out of a battery, or you can have a radio frequency current. But either one, if you double the resistance, you cut the current in half. Here's a graph showing the effect, basically how much the resistance, the effect of resistance as a function of frequency. As you go from zero to high frequencies, this white line represents the resistance. And the yellow squiggle is how much current you get at different frequencies. So this is a low frequency signal. Here's a high frequency signal. And they have the same amplitude. They're just different frequencies. Now, that's not going to be true for the capacitor and the inductor. There's a term that, it's impedance. There's a term that is used in everyday life very similarly to resistance, but when we come to electricity, it has a specific meaning. Impedance, electrical impedance, is represented by the symbol Z, is equal to something called resistance of resistors, just that's like a wire, whatever, that's what we've discussed so far for the letter R, and reactance. And even though reactance starts with an R, it's represented by the letter X. X sub L, here's that inductor symbol again. Here's the capacitor signal. So this is the inductive reactance. This is the capacitive reactance. So impedance is the resistance. Effectively, it's resistance from the resistor and the reactance from the inductor and the capacitor. The mathematical expression for those is this. Z is equal to the square root of the sum of resistance squared and the square of the difference between the inductive and capacitive reactances. Something else to know is that there's a difference here. The voltage across a capacitor in your circuit and the inductor in your circuit are always 180 degrees out of phase. That means when the voltage or the current going through one of the capacitor is on the rise, over in the inductor, it'll be dropping. So if we can set up the situation so that the voltage across the capacitor equals exactly the voltage across the inductor, and they're opposite, they will cancel each other, and they'll have equal amplitude, and they'll cancel each other when we have this condition called resonance of the circuit. That means we have, an inductor can interfere with our current flow. So can a capacitor, but if we set these just right, we can have them cancel out, and we're only left with the impedance equals the resistance of the wires or whatever components we have. So we have the voltage across the capacitor, the voltage across the inductor, they cancel, and all we have is it's a minimum resistance. That's the minimum impedance of the system. That's where there's going to be less obstruction of current flow and our signal. So we can transmit efficiently and we can receive efficiently when we meet this condition. Okay, so here's another drawing of that same thing I showed you before, except I've left out the inductor. Here's our voltage source, here's the resistor, here's the capacitor. So what happens at different frequencies? Well, in a DC circuit, suppose you have a battery here. You have the positive terminal hooked up to one side and the negative terminal hooked up to the other. And there's always a resistor because your wire, unless you're superconducting, your wire always has some resistance. Now, there's a plate with air across it. So unless you have a super battery that's going to create an arc and jump across here, this is effectively an open circuit. It's as if there's no connection between these two wires. So nothing is going to go through. This has very high reactance. Doesn't matter what your resistor is. Nothing's going to flow across this terminal, these terminals. So you get no current able to flow, therefore very high reactance, and therefore high impedance. All right, now what happens if we start? We start with a very slow oscillation. Well, if you want to measure how much current's flowing through a segment of wire, we push some this way, and we're pulling here. We push some here, and then we slowly push it back the other way, and back and forth. So that means that if you're measuring a current through the wire, you're going to see it go up and down, and up and down slowly as we oscillate this. Remember, with the battery, you turn it on and nothing flows because all you're doing is pushing up against an open end. Now, if we oscillate the current, we can get some flow. When you go faster, you end up with flow here, and when you go infinitely fast, imagine you're pushing back and forth very, very quickly on this. There's effectively all the time there's going to be some current flowing in the wire. So that means that as you go higher and higher in frequency, the reactance of the capacitor drops. Here's the expression for what I just described. The capacitive reaction is 1 over 2 pi times frequency times the capacitance of your capacitor. So the 2 pi is just a constant. F is the frequency. So if you're talking 123 megahertz, that's one thing. If you're talking 0 megahertz, that's a battery. And the capacitor, these are measured typically in picofarads. Farads are units of capacitance, and we're usually dealing with picofarads when we design our coils. So 1 over 2 pi times F times C. We're going to have to come back to that equation later. Now we have an inductor. What happens in the same scenario? We have is a resistor, an inductor, and the voltage source. Well, let's hook up a battery to the system. The current pushes here, it starts to push through, and now as it goes through, remember, whenever the current flows through a wire, it generates a magnetic field around the wire. So if you generate a magnetic field around this, and as the current pushes through, imagine when you hook up a battery, this happens very, very quickly. But if you could slow down time and monitor it more easily, you'd see the current pushing through here and generating magnetic field around the wire as it goes. But then as each loop is surrounded by a magnetic field, that magnetic field is interacting with the adjacent loop and actually opposing the current flow through here. So as the current develops through this wire, it has to overcome the reactance, this obstruction of the current flow as the magnetic field around the inductor develops. So at very low frequency, you just run the current through, and once everything is settled and all the magnetic fields are stabilized, the current just flows as if it wasn't even there. It looks no different than a regular loop of wire, except you could measure a magnetic field around it. Now, suppose we start to oscillate the current. We push through here, and we bring it back, and we push through here, back and forth. Well, every time you push, you're going to have to overcome a newly generated magnetic field. And this loop is going to oppose the previous one. And as you turn down the voltage, this magnetic field is going to tend to make the current in the adjacent field persist. So you have it wants to slow down the whole process of rise and fall of the current. Now, imagine you go to very fast, very high frequency, push and pull, and push and pull. You're always going to be encountering some opposition to the changes in the current through this loop. And so, as you go up in frequency, there's more and more reactance. It impedes the flow of current through the inductor. And here's the equation that expresses it. Again, my frequency is very low. The reactive inductance is very low. If this F frequency is 0, you have no reactive inductance. Not after that initial push of the current through. After that, it just stays the same. And as the F goes up, then the reactance of the inductor rises, and so the reactance of the inductor rises. So the impedance of the circuit would tend to rise if you just have an inductor in the system. L is the symbol for inductance. And inductance is measured in units called henries. You normally will not encounter any discussion of henries when you read about MR studies. Okay, so now we come back to this equation. We want a situation where the impedance Z, the impedance Z equals this expression, and we want a situation where these two things, XL and XC, are equal and cancel, leaving us just with the R. That's what we want. XL equals XC. That means Z equals R. And that happens when, say, XL equals XC. Well, let's plug in the equation for XL and plug in the equation for XC. That condition, we want a condition where the values of L and C are such that 1 over 2 pi times LC, square root of LC, equals the frequency. So we know we want to work at the Larmor frequency. So at 3T, downstairs we're talking 123 megahertz, 2.89 Tesla. We want to choose L and C so that they meet this condition, and our circuit behaves very easily for transmission and reception. Now the value of L, we don't typically fool around with that. L is something that usually just happens because of the size and shape of the object. If you want to build a head coil, you need to build a circuit that has conductors configured so that they will interact with all the parts of the head that you want to see. And then it's up to us to choose the value of C to make this equation match for the Larmor frequency. So we have a combination actually of fixed capacitors, which I'll show you in the photographs, and adjustable capacitors. So we can set this coil up to function just fine sitting on an electronics bench when we build them. But as soon as someone puts their leg in it or their head in it, the object becomes part of the circuit. And we have to then we have to be able to adjust the value of C to compensate. So we use adjustable capacitors to adjust the value of C so that we get this condition met once again. C equal the XL. So before we do an experiment, we attach the coil to a frequency source, and then we measure its impedance while we're changing the tuning capacitor. And when the tuning capacitor becomes purely resistive, when the impedance becomes purely resistive, and another condition I'll talk about in a little bit, it reaches 50 ohms, then the coil is tuned. So this 50 ohms, there's something called impedance matching. It has to do with efficient transfer of energy. So we want the coil to resonate, to have its purely resistive behavior on resonance. But we also, at that point, we want it to look like a 50 ohm load. So in this video from YouTube, physicsanimations.com, there are two balls colliding. When they have equal mass, there's a pure energy transfer from one to the other. When the masses are unequal, it becomes inefficient. Here you get reflective power. I'll show that again. They are matched for mass right now. Here they are not matched. You don't transfer all of the energy from the source, the green ball. And here, again, you don't transfer all of the energy. You actually reflect some back. So we want to match our circuit. Electricity behaves in an analogous way. We have our source. Source has some resistance in it. There's our voltage source. We have an inductor, and this is our coil. We have this impedance and our resistance and our capacitance across the inductor. They have to both behave like 50 ohm loads, or there will be power reflected. If they are not matched for 50 ohms, then what we transmit to the coil, some of it's going to reflect back to the amplifier. And at a minimum, that creates a situation where you've got to run the amplifier harder than you would otherwise. It takes more power to get through the coil, so you need a bigger amplifier. What's actually a more serious problem is that when power reflects back from the load, from our coil and head, to the amplifier, you can actually damage the amplifier. I'm back in the 90s. That someone was telling me about their visit to a lab where they could hear the amplifier, and every pulse the amplifier was emitting a bang. There was so much reflected power because the circuit was not set up properly. So I imagine that amplifier didn't last long. So when we have impedance matching, because we have more efficiency, it goes both directions, transmit and receive, we can use shorter pulse widths. More of the power gets to the coil. We don't waste things reflecting back to the amplifier. We don't have to put out as much power from the amplifier to get the same result. And I've only talked about power reflected to the amplifier. We have this very weak signal coming back from the sample to our receive path. If those aren't matched, then some of the signal will reflect back to the sample, where it does no good. It won't. The signal's so weak it won't do any harm to the person. It'll be undetectable practically unless we had sophisticated electronics here. But whatever of that tiny signal doesn't make it to our receive path, that's signal loss. That's in NMR we need every drop of sensitivity we can get. So each component, the amplifier is set to 50 ohms, the cable is set to 50 ohms, the probe is set to 50 ohms. The reason it's 50 ohms isn't magic, it's historical. I believe that radar used 50 ohms as a matching convention. Your cable television at home has 75 ohms as a convention. The cable, all the connectors, if you just make a connector yourself, it's likely not to have very efficient power transfer for your cable TV at home because it won't be built to the same impedance. So all the components, if you want to replace a connector or something on the magnet, when you go to the store to buy one, you're going to have to ask for a specialty store and ask for 50 ohm connectors. Okay, so now there's another aspect to consider. It's called the quality factor of a coil. It is the power absorbed over the power lost. So you want the sample to be absorbing the power. You don't want to lose power. That's one aspect. Another is that you want the sample to interact with the coil, because if you have an inductor that's supposed to create a B1 field through the sample, then it's going to have to interact with the sample. So in practice, we measure the Q from the change in the width of the frequency response of the coil, according to this equation. So Q is equal to the F, is equal to F over the full width at half max. And we want to see how much the Larmor frequency doesn't change. We want to see how much the full width at half max changes. So here's our delta F, that's our full width at half max. When you design a coil and you see how the current responds at a band of frequencies, maybe this is alarm, maybe this is 123 megahertz, and over here is 122.8 megahertz, 0.9 megahertz. You get a drop off as you move away from the Larmor frequency. You want to see how quickly it drops off. So you have one configuration when the coil is just sitting empty, and you should have a noticeable change when you put someone's head or whatever sample you're using into it. The frequency response should get wider, and the current should go down. You should have a definite interaction with the sample. So if you were to take a surface coil and to empty, measure it on the bench, and then you put some saline in it, you're going to see, if its coil's built properly, so the coil that has a B1 field through the middle here, you should see a marked drop-off in the Q. And the distilled water, if you take a container of distilled water, which that actually, water has no conductivity in it. It should interact very little with the coil. So if you put pure distilled water in a container, it should look pretty much like air, and you get no reaction. A person is going to be more like saline. Not 100 millimolar, but a person will be more like saline, and you should see a reaction to this sweet width. Okay, so here are some pictures, some examples. I'll start this video in a moment, but I want to point out these are surface coils. In the middle, we have a surface coil where the circuitry, the capacitance has been set up to make this circular inductor resonate at 175 megahertz. This is meant to operate on the 4 Tesla. And here, these are 2 coils designed to resonate for phosphorus, so at a much lower frequency. Now, each coil has, these are ceramic capacitors. So the middle part, the cream-colored pieces here, those are ceramic, and the metal here are the connectors to the wire, and plates, metal plates on each side of the ceramic. So the ceramic is designed so that the current can't flow across here. Ceramic's generally a pretty good insulator. If you've ever seen an electric fence out and around the field, they have the wooden posts or metal posts with ceramic insulators, and the electric wire is wrapped around those insulators, so to discourage the cows from walking out of the field. Don't touch them. I've done that. It'll knock you over if it's set too high. But here's our inductor for proton, inductors for phosphorus, and phosphorus set up on separate circuits. Now, the wires go back here. See these 2 cylinders? Those are adjustable capacitors. These are fixed capacitors. When the coil's built, the engineer who built these chose capacitors to get the coil close to the Larmor frequency. And then every person that goes in affects it a little differently, so we adjust capacitors here. All right, I'm going to start this video now. There, that's phosphorus. It has an adjustable capacitor there. You can't see it. Oh, yep, here's one on the other side for the phosphorus. More fixed capacitors. Now we go back. There's the capacitors, and this. See these 2 cylinders, these 2 light-colored plastic cylinders around the yellow cable? They are called tuning rods. They connect to, one's a tune and one's a match to adjust the performance of that circuit. Here's the cable that connects to the transmit and receive lines. So this set, because there are multiple nuclei here, this had more circuits. I'm pausing the video here to show this is a quad. It's called a quadrature hybrid. What's inside this box, shielded under some copper, is something that shifts a signal by 90 degrees, or what's coming out of the amplifier to both sides. We're not going to discuss the quad hybrid today, but those two phosphorus coils are driven in what's called quadrature mode. That single proton coil is driven in linear mode. All right. So the next component we have is now that was a human coil for head or leg. Here is one for from the animal system, intended for rat or mouse. This small coil we're seeing edge on, that's a circular loop of wire, circular surface coil, that sits right on the animal. There, you can see it as I turn it over. Here are adjustable capacitors, and here here's a fixed capacitors. A fixed capacitor right here, a ceramic capacitor. It's very small because this is a very small coil. Back farther along the structure, you can see the scale of the coil with my finger. We go on past these tuning rods and a little electrical cable that connects it all. Here we are approaching the end. There they are, the tuning rods. Surface coil tune and surface coil match. Tune and match. So one of them sets the impedance to be minimum on resonance, and the other sets the impedance to be 50 ohms at that minimum. They generally interact to some extent. So change the tune by going back and forth. And these coils, for most of what we do here in our center, we have to build our own coils for the animal systems and the 4T and 7T systems. Next coil we have is a volume coil. This is also for animals. So you see inside, there's a pencil, and you can just make out inside there's some bars. I'll get a better look for you there inside. See these metal bars? That looks like a bird cage. Talk in a few minutes. That's a bird cage coil. Go down through the tuning rods. The axis, this cylinder goes into the scanner, and we have to access them through long tuning rods. We're going to tune once the subject or the sample is in the scanner. There's the view of those rods inside. As I say, it looks like a birdcage coil. And now we'll show you the tuning and the matching. This is called a Morris sweeper. Morris is the brand, I believe, but it's a sweeper. It's called a sweeper because it puts out a sweep of frequencies. In this case, for the 11.75 Tesla magnet, we're talking about 500 megahertz, so much higher than the 3T or the 4T. You can change the bandwidth. You can change what Larmor frequency you want. There's a cursor you can move around. Right now it's set to be optimum for this scanner. This is the nominal Larmor frequency for it. It may vary a little bit from chemical to chemical, but it's going to be around that. So I'm going to take a coil and hook it up. That same coil. I'm going to hook up the proton cable to it. There we go. That's deuterium. We hooked that one. That was 2H. 1H. We hooked up, so we're hooking up the 1H now. There we go. Now see, we want it to be at a minimum right at the cursor in the middle of that line, but it's not. So I'm changing the tuning rod to move that, change the capacitance, and as I do, there it is. As I do, it gets pushed to the minimum. We want that to be as low as possible also. So we'll move that. Yep, that's it. Now, it does interact. It's empty right now, but watch how it interacts when I put something, put tissue inside it. So When I put my fingers in and bring them out, it changes the behavior of the circuit. So I would need my arms are long enough to put my fingers in there and tune at the same time. But that's exactly what you need to do if you wanted to run a scan on a sample. Okay, next we talk about noise. Now electrical noise comes from vibration of atoms. Just as we've said that an electric current moving through a wire generates a magnetic field around the wire, and well, the reason that happens is that you've got electrons moving, they're charged particles, and when they move, you see a change in the magnetic field around those particles. So if you have electrons all moving in the same direction or a net direction through a wire, you get a net magnetic field, very coherent. If the electrons are just bouncing around like they do all the time, anytime you're above absolute zero, the electrons are moving around. Each electron is generating its own little magnetic field, and that has an impact. You get millions of Avogadro's number multiplied by several times, full of electrons bouncing around. You will get randomly generated magnetic fields, and some of them are going to be around the Larmor frequency and others not. The ones that are near the Larmor frequency actually appear as noise in our spectrum. So this comes from random motion of electrons. When the temperature rises, you get more motion. So if you have some wire that gets hot, that heat is occurring because the atoms are moving around, hitting things. Electrons are running into things and that's like transferring kinetic energy, and it gets hot. If you touch it, some of that heat and that energy gets transferred to your fingers and it burns. But it also increases the noise. So increased vibration of the atoms generates noise, and the noise is random. It's random voltage. We pick that up. The noise equals the square root of this product. So we have 4 times K, Boltzmann's constant, times T. That's the absolute temperature in Kelvin, times the frequent receiver bandwidth. That's actually how quickly you are sampling. How many samples per second are you getting? And then the resistance of the wire. So if you have high resistance wire, you get more noise generated in it. If you are sampling at a faster rate, you have more opportunity to pick up noise. If your temperature is higher, you will pick up. There's more motion of the electrons, so you pick up more noise. And these things come into play in different ways in different scenarios. So first we'll talk about the noise in the wires. If you have wire that's very skinny versus wire that's very wide, you get more noise and more resistance in the thin wire. Imagine that you were to think in practical terms. If you were to go outside your house and replace the main cable from the street with a little tiny electrical wire like you might find inside a radio, you can imagine that probably wouldn't work so well. I suppose it would melt the wire almost immediately, but it would be extremely high resistance. So a thicker wire helps to decrease the resistance. You can imagine if you're going through a little tiny wire, or you've got to go through a very long wire, the long wire also gives more opportunity for noise. There's going to be more electrons, there's more material. So if you have a coil that's really large, that coil will generate more resistance than a coil that's a little tiny coil. And this is true whatever frequency you're working with. But something else, as you go up in frequencies, you start to get some behavior you don't normally think about. One is called the skin effect. It's easier for the electrons to pass along the surface of a wire than it is for the middle when we're dealing with high frequencies. So the wire, in that case, you want some kind of a conductor that has a lot of surface. I've seen wires that are actually tubes, hollow tubes, so now you get surface on the inside and the outside of what you see. There's a very common, like if to have sheets of conductor for your coils. If you ever get a chance to see the inside of one of the commercial coils, you will find some of the circuits are actually flat sheets. So you get a lot of surface. Now, one of the consequences of the sheets, though, suppose you've got a birdcage arrangement where you've got adjacent rungs of, like, remember the animal coil that I showed a few minutes ago, where you could see inside this little cylinder there were bars that ran the length of the cylinder. If you get those too close together and you operate at a high frequency like 500 megahertz, these electrons flowing through here around the surface will generate a magnetic field around the surface like they're supposed to. That's what we need them to do. But that magnetic field doesn't just interact with the sample, it also interacts with adjacent wires. And it impedes the flow of electrons through the adjacent wire. And so it pushes the current. They can't flow so well through here, so they go to the opposite side. And all of a sudden you've made part of the wire unavailable, or made it more difficult anyway for the current to flow through. And you get the same thing in it goes both ways. So if you put two of these next to each other, you can have a situation where you don't get efficient current flow where they are close together. So the geometry of your circuit really you've got to think about it in relationship to what frequencies you use. So unless you end up building coils, you won't have to worry about it, but it is important that you know these. If someone sells you a coil and you see that the bars are very close together, you may want to ask them about it. Sometimes it's good to have some proximity, other times not. Another contributor to noise, we really focus on noise in NMR because per atom, NMR is pretty insensitive compared to, say, PET. So we really need to be very careful with preserving our signal relative to the noise. So we want to consider the materials that we make, the wires that we make things out of, how the circuits are configured, but we also want to look at sample noise. So we have our inductor around the coil. If you have a big sample, the sample also has electrons that are bouncing around and moving. And you can't really, when you're working in vivo, you can't really control the temperature of your sample. You want to keep the person comfortable. You don't want to cool them down. So you may have a large sample that has a lot of random electric noise, and that's just something we have to live with. If you have a very small sample, then there's not much sample to give you electric noise, and that means the circuit dominates. So there's some things that we can do to improve if anything you can do to reduce the noise in the circuit can have a dramatic effect when you have a small sample. When you have a big sample, yes, you should have efficient circuits, but the impact is not so crucial as when you have a little tiny sample. We also get capacitive interaction of this sample with the coil. And that's one of the things we have to consider when we design the coils. What range of capacitors do we need? Sometimes you'll see a coil that's built, so you can't tune it unless there's a sample in it. And the reason is that with a sample in it, the capacitance is so different that we can't. It's not practical to put an adjustable capacitor that lets you do it both ways. So this is a little bit off topic. We're not talking about noise, that's capacitance. But what the most important thing about the noise here is when your sample is big, it's likely going to dominate as a source of noise. When your sample is small, then your coil is going to play a significant role as a source of noise. Then the third factor that contributes to noise is called far field noise. So you have, say, around 60 megahertz for 1.5 T, 170 for 4 T, 500 megahertz for 11.75 Tesla. You get your coil in the scanner. And then you have somebody lying in the scanner with their feet sticking out here. There's a scanner, that's a magnet. Well, meanwhile, what we have going on is the radio that you listen to for music, FM band. Well, that's a lot of noise, and they just, if you're working down at some of the lower field superconducting magnets, you're in this band of radio noise. Um, it's all around us. If you like to listen to music during the scan and you can turn on the radio, then there's radio noise present where you are. Television, not so much an issue anymore, but for television, but the frequencies, when they went to cable TV, the frequencies were used for other purposes. So there's TV. What was TV formerly is used for a lot of different. It's used for a lot of things that can also end up contributing noise to your scan. And then this is a really old cell phone, but cell phones are very high frequency. They're mostly going to be out of range, but they still can contribute noise below. And then there's a space station. Probably not an issue for us. So we put the whole thing, the whole scanner, inside a Faraday cage, because it's you got the coil here, and the person lying there, their feet and their body sticking out of the bore of the magnet can actually work like an antenna and draw noise in and into your coil and give you noise in your sample. So the Faraday cage is a sealed electrical box. And if you get down in the MR center, you will see that the doors, I'll show you a picture in a minute, the doors actually have electric clips on them. The walls may have some holes in them to let electricity in and out and for tubes and things to go through, but they are very specialized, and I'll explain that in a moment. It's when you scan, it's important, it's very important to keep the door closed. Not just from a safety perspective, because of keeping people from walking in with metal objects that don't belong, but also to keep the radio noise out. Okay, here's a little video of one before I started. I want to show you all these electric clips along this door. It's a very heavy door. You have these electric clips around it, and you may notice it's a little resistant to push. It makes a squeaky noise because it rubs up against the electrical contacts on the door. And there's all the electrical contacts all the way around the door. Now, look, see where they rub up against the electric? This is what you can see of the electric metal box. See all these this way where the metal's worn? That's from the electric clips rubbing up very firmly against there when the door is closed. So you got to keep the door shut to keep this electric sealed. It didn't photograph well, so I couldn't show you very well that the window of the scan room is also, it looks a bit hazy when you look through it. And if you look very closely, you'll see that there's a copper screen embedded in the glass. That's so that we don't have a giant electric hole where the glass in the window belongs. So there's a compromise. You got a glass window and it has screen inside, so you can see through pretty well. But we had to maintain something in there to keep the electrical integrity of the room. Now this room, now what I'm going to show you is a video of what's called a filter plate. This was built by our engineering staff, Terry Nixon, Pete Brown, Scott McIntyre, in the MR Center. If you buy a commercial system, I suppose it'll come with its own filter plate from the manufacturer. And it's a filter plate because if we just take an electric wire and run it through the wall, through a hole, into the scan room, first of all, the hole can emit radio noise. Second, that electric wire, which is usually 60 hertz, will introduce 60 hertz noise into our scans. You can actually, I've seen this happen where we have spectra, and every 60 hertz, there's a noise spike. Or there are images that have vertical bands through them, or horizontal bands, and the separation of those bands corresponds to 60 hertz spikes that come from just commercial electricity outside the center. So we have to run them through filters to get to avoid having noise injection into the room. All of those connections, those plugs, there's something coming in from the outside of the room, and you're looking at the inside of the room with all these plugs going in. There's something else that didn't come out well in the photographs, but it's called waveguides. Sometimes we do injections from outside the magnet room. The injection pumps that we use often cannot go into the scan room. So that equipment has to sit outside the scan room. It could be an issue of safety, or it could be because they are operating with an electric motor that would cause noise in the images. So we have to run the intravenous infusion tubing through the wall to the subject. Well, we can't really filter that. It has to go through a hole. So the hole is set to have a particular diameter and length that will filter out. It will not permit the relevant frequencies that we observe to pass through the wall. So if you come to the console rooms and look down near the floor, typically, you'll see what look like little stubs of pipe sticking out of the wall around a hole that's big enough to put some infusion tubing through. And that's why. Now we'll talk about some different types of coils. Variety. We have surface coil I've talked about extensively. I like to use that in the drawings because it's such a simple circuit. You also saw some video of a large surface coil for a head, or a human head, or a leg. You saw a very small surface coil we used for a rat or a mouse. You saw a birdcage coil that was from the animal system. That was the one that had the little bars running the length of the cylinder. There are also saddle coils. If you ever do analytical chemistry on a vertical bore magnet, that's likely the coil that you will be using. You won't see it because it's down inside a cylinder, but that's what's down in there. And then there's solenoids, very simple coil, but effective, homogeneous B1 right through the middle of the cylinder. You saw a quad coil with a linear coil. So here we had, what it was in that picture was a proton linear coil and 31P, phosphorus 31 quad coil. You can do other configurations though. Like here, you could have a proton quad coil and a C13 surface coil that's driven linearly in the middle. The first coil that I showed you, sitting on the magnet bed at the very beginning of this video, both of those coils on the bed were phased array coils. That's an array of coils set to go around. They may not be circular, but it's an array of coils set to go around the object, or maybe you could have them lying flat as a sheet if you want to do spine imaging. But you have an array of coils, each one transmitting separately, each one receiving a signal separately, each one going through its own preamplifier and back to the computer. The computer, we make some measurements so that we know how correctly to combine the signals from each of these. And this going to phased array has greatly enhanced sensitivity for a lot of studies. The birdcage, you can also combine these two. You can have a birdcage transmit and a surface coil receive. Pete Brown in the MR Center has built some of these. They're very effective. The reason you might want to do this is to have a very homogeneous B1 and a very sensitive detection in a particular area. So you try to get the best of both worlds with these different configurations. So the surface coil is wonderfully sensitive nearby. It's not so sensitive far away, because you imagine if you had a piece of wire, you ran electricity through it, you measure the electric field near the wire, it's going to have a higher magnetic field than if you measure the electricity far away from the wire. The same thing with the surface coil. If you are within about a coil radius, it's optimum for sensitivity. After that, the sensitivity drops off pretty dramatically. Now you have to have in any coil you use, the coil can't go in the magnet in just any orientation. It has to be oriented so that the B1 field that it generates is perpendicular to the axis of the magnet. It doesn't matter if it goes sideways or up and down compared to if in a horizontal bore magnet, but it can't go along the direction of B0. If we were to turn this surface coil on its side, so you had a loop placed vertically, we wouldn't be able to get a signal. You could put power in, you could tune it, but the B1 it generated would be completely ineffective at rotating the magnetization out of the XY plane, and also at detecting a signal, because the signal is the signal comes back from precession perpendicular to the B0 plane, and if your coil's not in the right orientation, you won't detect that. So here's showing the B1 dropping off as you move away from the center. Something else to notice, that coil, I keep drawing a circular coil in my drawings, but the coil you saw had capacitors inside the loop. It helps to reduce some electric fields. It also can break up wavelengths. Sometimes when you're working at a certain frequency, every frequency has a particular wavelength associated with it. And as the wavelength becomes similar to the dimensions of the coil, you could get something called standing waves, where you get resident low intensity in one place and high intensity somewhere else. So you can help make coils run more efficiently by breaking up the copper lengths and putting distributed capacitors across them. Here again is a B1 inhomogeneities from a surface coil. This graph from 1992 shows you get very intense radio frequency up close, and it drops off as you move away. This is in terms of coil radius, 1 coil radius, 2 coil radii. Now note that if you ever see one of our coils up close, the surface coils, you will see that they are covered with a layer of plastic. That prevents people from getting right up against the wire, because the B1 is very intense, and you don't want to risk the chance of giving too much energy to the skin. So we have a little bit of a distance here so that we can do the experiment at the depth we need without depositing energy in the skin. It's just plastic here instead. If we look along the X direction, XY, so in this top graph, the bore of the magnet is in our line of sight. We're looking down the bore of the magnet, and there's the X and the Y. Now if we look sideways along the bore of the magnet, Y is up, and the X is down our line of sight. Here's what the magnetic field shape looks like. So really we're optimal for what's going on in the center of the coil, which is not surprising. So the Helmholtz, this is a Helmholtz coil. This is a saddle coil. They have very good homogeneity down through the middle. So imagine the B1 flux lines going right down across the raft here. Well, here the B1 is designed to go up and down. This is what you would find to put an analytical sample in. You put it inside, the coil sits inside the vertical bore magnet. You put your sample in a holder that can sit on a cushion of air, and then you tell the computer to drop your sample in, and it will slowly reduce this air cushion until your sample slides neatly into the saddle coil. They do protein solution, brain extract, any kind of a test tube experiment. Here's the bird cage that I showed you before. Now here's a phased array coil. Oh, we're coming back to the bird cage. Bird cage has the conductors going all through here. As I mentioned, you can't have them too close together, but you need enough of them so that the B1 field around here will penetrate and somehow combine to make B1 everywhere inside the brain and allow you to receive a signal from anywhere inside the head. They are designed to have pretty good homogeneity. In any specific place, they won't be as good as the surface coil would be in that place, but they let you see everywhere with reasonable homogeneity. So these are very good for imaging. Generally, today, it's mostly phased array coils that are used for human head imaging. So here there's only 4 circuits for demonstration purposes. The coils that I showed you before, with our scanners, we have 20, 32, and 64 channel head coils. So here are 4 phased array coils. Imagine they could be circular or rectangular, some kind of coil. They go through 4 independent preamps, 4 receivers, 4 analog to digital converters, and the signals are stored separately on the disk. And then the software, if you end up working out your own and acquisition routines, you'll have to write your own software for combining them. For what's produced on the scanner, you generally won't even be aware of this part. Your signal will just come back and be already assembled for you. And this is that automatic part is we do a Fourier transform of each part. They have to get phased and summed um, according to some measurement that we take to measure the relative efficiencies of these coils and their relative phases. Remember we talked about how the signal can, when you open the receiver, you can have the signal arrive at the detector with different locations in the XY plane. And the uh, the detectors for each of these detectors has a different distance from every part of the brain, so the phases for every part are going to be a bit different. Phases for every detector had to be a little bit different, and so we measure what they should be, and then phase the images, phase the spectra, add them together to get something that makes sense. Here's an example, pretty simple, with just four coils for a spine image. You could take an image and then move the patient or the coil, take an image and take an image and take it. You do it that way. Or you can use the phased array, all of them at once, and get the full spine in one shot. So there's a clear benefit. Now when we get down to um, the coils, the coil versus the sample size, remember I said if you've got a small sample, sometimes it can pay to invest a lot of effort into reducing the noise that comes from your coil. And there are supercooled, they're not they're not liquid helium, but they're liquid nitrogen temperature conducting, liquid nitrogen temperature samples. So you can really drop the resistance and therefore the noise. These coils will have, say, a copper sheet, and you a thin, you can have, well, copper coil itself, or you can have thin film, high temperature superconducting coil. So you get down to liquid nitrogen temperatures instead of liquid helium, and eliminate the noise almost completely. So whatever noise is coming back from your sample. It's an engineering feat because you have to keep the coolant flowing, and you heat it. You don't want to freeze your sample, but it can be done. So to summarize, the NMR coil consists of an inductive capacitive resistance. That's an RLC circuit. That would actually be RCL, the way I've written it, but they call it RLC circuit, that can be made to resonate at the Larmor frequency. And we do that by, we build the coil that, because of the coil geometry, the sample we want to get, it has a certain inductance. We are generally stuck with that. And the wire has some resistance in it. And all the materials have some resistance. We adjust the capacitor. Now, fortunately, it has a little bit of breadth, so you can do imaging where you may be 10 kilohertz away from the average Larmor frequency in the scanner. But it'll still perform well there. So when we have the reactances for the induction and the capacitance equal, we are in a condition called resonance, and that is where the coil behaves at maximum efficiency. And we need maximum efficiency for the best power transmission, for B1 generation, and for the most sensitive signal reception. So that way the coil provides the means to transmit and receive radio frequency to and from the sample. To design those coils, we have to consider the resistance of the materials. So don't use too much wire. While we're on the subject of wire, we actually can't just whip out some copper from the hardware store. We have to use high purity copper because the regular copper you may buy, it often contains trace ferromagnetic impurities, which don't matter for most electrical work. But for our environment, you don't want anything that's going to disrupt you don't want something that's going to create a T2 star effect if you can avoid it. So, but we consider that primarily for the electrical behavior of the circuit, we're interested in resistance, capacitance, the inductance, and different types of noise. So the noise can come from the coil, and if you've got a small sample, that dominates, and you really want to put some effort into reducing coil and noise of the coil. It can come from the sample, especially, and it always comes from the sample, but if you've got a big sample, then that's what dominates. And then there's a general environment. So the bottom line is keep the door shut to the magnet room. It makes a big difference. Then a variety of coil designs have arisen for specific needs, and people are building new coils regularly. There's a whole literature on new coil designs. Some are very specialized. Some people are trying to take general purposes and make everything work better. Um, so surface coil, the big drive is to get sensitivity and homogeneity over the sample volume of interest. Surface coils give you high sensitivity near the coil, but when you get more than a radius away, the sensitivity is poor. Uh, Volume coils give you lower sensitivity than you can get with a surface coil, I mean, close to where the surface coil is, but they give you decent sensitivity over a whole head. So if we wanted to measure some minute metabolite, we might have to do a surface coil study in a region close to the surface of the brain. Um, but if we wanted to take an anatomic image because somebody just had a car accident, we would want a volume coil, not a surface coil. The general design challenge is to give optimum signal-to-noise ratio in a given volume of interest. Could be a muscle, spine, could be the whole brain. But that's the purpose. That concludes the lecture on coil design.